I want you to imagine something very simple. So simple, in fact, that nobody ever worries about it. You're standing in a room. There's a table. On the table is a glass of water. You look at it, you reach for it, you pick it up. End of story. Nothing mysterious. No angels, no demons, no equations crawling out of the walls. Just a glass of water behaving itself. Now here's the odd thing, physics has absolutely no idea how you managed to do that. Oh, it can tell you plenty of impressive things. It can tell you about electromagnetic forces holding the glass together, about quantum fields buzzing underneath the surface, about probabilities and amplitudes and interactions. It can give you formulas so accurate they'll make your head spin. But the actual event, the fact that you saw the glass there, decided to pick that one and experienced it as a single, solid, ordinary thing, there's a gap there, a quiet one, and most people don't even notice it. That gap is what I want to talk about. Because if you stare at it long enough, it starts staring back. Here's the paradox, and it's a beauty. Quantum mechanics, the most successful theory ever invented by human beings, insists that the world is not made of things, but of possibilities. Clouds of maybe. Numbers that tell you what might happen if you look. Yet the moment you do look, you never see a cloud of maybes. You see one thing, one outcome, one glass, one click in a detector, one world. Where did all the other possibilities go? This isn't a poetic question. It's not philosophy for armchairs. It's a brutally practical problem. Every experiment we run, every transistor in your computer, every laser, every atomic clock, everything works because the equations deal in superpositions, sums of alternatives, and yet your experience stubbornly is singular, definite, downright boring. Something doesn't add up. When I was younger, people would ask questions like, does the electron really go through both slits? And I'd say, that's not a bad question, but you'd better be careful, because your words may be sneaking in assumptions you didn't notice. Physics is full of that kind of trap. You think you're asking about reality, but you're actually asking whether reality behaves like your mental picture of a little billiard ball with an identity crisis. The equations don't talk about electrons as things. They talk about amplitudes, and amplitudes don't live in space the way tables and glasses do. They live in a mathematical space that's far stranger and far more abstract than anything you can point to. Now here's the curious part. We teach quantum mechanics as if the weirdness is all in the small stuff. Atoms, particles, tiny dots dancing to spooky rules. But the real weirdness isn't that electrons behave strangely. The real weirdness is that tables don't, because tables are made of electrons. So why don't they act like it? You might say, that's because of size. Lots of particles average out. That's a good instinct. It's not wrong, but it's incomplete. Because averaging doesn't eliminate possibilities. It just hides them. And hiding is not the same thing as explaining. Here's a little thought experiment, no fancy equipment required. Close your eyes and flip a coin, heads or tails. When you open your eyes, you see one result. But before you look, did the coin have a result? Classically, we say yes. Quantum mechanically, we say, well. That depends on what you mean by have. Already you can feel the language creaking. In quantum theory, before observation, the coin, if it were truly quantum, would be in a combination of heads and tails, not undecided, not secretly one or the other, both at the same time, and yet when you look you never see both, ever. No one has, not once, not even on a bad day. So something happens when observation enters the story. People call it collapse, which is a wonderful word because it sounds like an explanation while explaining absolutely nothing. Collapse of what? Into what, according to which rule? And where exactly does this collapse take place? In the coin, in your eye, in your brain, in the universe's sense of embarrassment. If you push too hard, the answers get vague very quickly, and this is where most people stop. They say, don't worry about it, shut up and calculate, which is fine advice if you're trying to build a laser. But it's lousy advice if you're trying to understand what the theory is actually saying about reality. The hidden gap isn't in the math. The math is immaculate. It's in the story we tell ourselves about how the math turns into experience. We assume, without noticing, that there's a clean boundary somewhere. On one side, quantum weirdness. On the other, classical reality, solid facts, definite outcomes. But the theory itself never draws that line. It doesn't even hint at where it should go. That's strange, because nature is not supposed to depend on where we draw our boundaries. If the universe really runs on quantum rules all the way down, and there's no evidence that it doesn't, then the emergence of a single, definite experience is not a small detail. It's the central mystery, the thing that should keep you awake at night, staring at the ceiling, wondering why the world is so obligingly clear when the underlying description is so gloriously fuzzy. And here's the part everyone missed for a long time. This isn't just about measurement, it's about meaning. about how information becomes something rather than everything, about why reality feels stitched together instead of smeared across possibilities. Once you notice that, you can't unnotice it. Every experiment, every observation, every result starts to look suspiciously like the end of a long, invisible negotiation you were never invited to observe, and that raises a dangerous question. Dangerous in the best way. If the equations never choose, but experience always does, then where does the choice actually happen? If you want, we can keep going from here, because once you start poking at that question, the universe begins to answer in ways that are, well, deeply unsettling. Good. Then let's keep our nerve and push a little further, because once you've seen the crack, you might as well look inside it. Suppose I give you a perfectly ordinary looking experiment. Nothing exotic, no glowing portals or humming machines, just a source that emits particles one at a time and a screen with two narrow openings. You already know the punchline, of course. Everyone does. Send the particles through slowly enough. 1, 2, 3, plenty of time between them, and still, somehow, an interference pattern builds up, as if each particle were interfering with itself. Now here's the part people repeat so often that it stops sounding strange. Each particle goes through both holes. That sentence is doing an unbelievable amount of work. Because what does goes through even mean here? We've borrowed a phrase from everyday life, a phrase that works beautifully for mailboxes and doors and people squeezing through subway turnstiles, and we've smuggled it into a domain where it has no business being trusted. The particle doesn't split into two little pellets. It doesn't hesitate. It doesn't peak. The math doesn't describe a journey at all. It describes a spread of possibilities, and yet, bang, a single dot appears on the screen. One place, not two, not a smear, not a maybe one. So let's try a different picture. Forget particles for a moment. Think of a wave on the surface of water. You poke the surface in one place, and ripples spread outward. If there are two gaps in a barrier, the wave passes through both and interferes with itself on the other side. That makes sense. No mystery there. But now comes the twist when you detect the wave. When you place a little detector at some point, it doesn't give you a fraction of a wave, it gives you a click. All at once. As if the wave had been patiently waiting to pretend it was a particle again. That's not how waves usually behave. Here's the uncomfortable truth hiding in plain sight. Quantum mechanics is neither a theory of particles nor a theory of waves. It's a theory of expectations. A machine for calculating what you should expect to observe, given what you did before. The wave isn't a thing in space the way water waves are. It's a bookkeeping device. A brilliant one, but still a device. And this is where the analogy starts to wobble, which is exactly where it becomes useful. Imagine you're blindfolded in a dark room, and someone is tossing darts at a dartboard you can't see. You hear a thud each time a dart hits. After many throws, you start keeping track. You say, most of the thuds come from the left side. Fewer from the right. You build up a probability distribution in your head. That distribution is not the dartboard. It's not even the darts. It's your knowledge. Now suppose this is the crucial step, that the universe itself keeps such a distribution. Not in anyone's head, but as the fundamental description of what's going on. Not a picture of reality, but a list of expectations about possible outcomes. That's quantum mechanics. And the trouble is, expectations don't explain experiences. They only predict them. The theory tells you with stunning accuracy how often each result will occur. It does not tell you why this result occurred this time. And it doesn't even try. It shrugs politely and hands you a probability. That's fine statistically. But experientially, it's bizarre, because you don't live in statistics. You live in moments. Here's where the hidden gap starts to widen. The equations evolve smoothly, deterministically, following elegant rules. No drama, no jumps, just a calm, continuous unfolding of possibilities. But your experience doesn't unfold that way. It snaps. One outcome replaces many. The world updates itself suddenly and decisively, and nowhere in the equations is that snap described. You might think, well, maybe it happens when the system gets big, when it interacts with lots of other things. That idea has a name, and it's a good one: decoherence. It explains why interference patterns disappear when systems become entangled with their environment. It explains why cats don't seem to be both alive and dead. It explains why classical behavior is so stable and robust. But here's the subtle catch: decoherence doesn't choose an outcome. It only explains why the alternatives stop interfering with each other. The possibilities don't vanish. They just stop talking. That's not the same thing as becoming real. If you're not careful, you'll think the mystery is solved when it's only been relocated. So let's try a more homely analogy. Imagine a gigantic library, so vast that it contains every possible book, every story that could ever be written, every variation of every sentence, every typo, every masterpiece, every piece of nonsense. Now suppose there's a machine that, when you press a button, hands you one book. You can predict the statistics of which kinds of books you're likely to get, but you have no control over which specific one appears. The library is the wave function. The book you receive is your experience. Quantum mechanics describes the library exquisitely. It tells you how many books of each type there are, how they're distributed, how they relate to one another. But the act of receiving one book, that's not part of the description. It's assumed. And assumptions are dangerous things in physics, because once you accept them without noticing, you stop asking the most interesting questions. Why this book? Why now? Why here? At this point, some people say, well, maybe all the books are real, maybe every possibility actually happens, and you just find yourself in one of them. That's a bold move. It removes the mystery of choice by declaring that there is no choice, only branching. A constantly splitting universe, with versions of you along for the ride. It's a clever idea. It may even be right. But notice what it costs. It turns the question inward. If all outcomes exist, then the mystery is no longer why one outcome happens, but why you experience this one. The gap hasn't disappeared. It's just wearing a different hat. What Feynman and a few others kept circling around wasn't an interpretation preference. It was a discomfort, a sense that something essential was being glossed over because it was hard to talk about cleanly. The theory worked too well to abandon, but too strangely to fully believe the story we told about it. And the key insight, easy to miss, is this: physics describes correlations, not experiences. It tells you how observations relate to each other, how probabilities line up, how information flows. But the fact that there is an experience, singular, immediate, undeniable, that's taken as a given. We don't derive it, we start with it, which means that somewhere between the smooth mathematics and the sharpness of awareness, something fundamental is happening that we don't yet know how to phrase. And once you realize that, the experiment with two slits is no longer about particles or waves. It's about why reality presents itself as a story with one ending instead of a book with all pages open at once. If you keep following that thread, and it's a slippery one, you start to notice that the same gap shows up everywhere, in time, in memory, in causality, in the feeling that no is special. And that's where things start to get really interesting. All right, then let's stop circling the edge and step straight into the deep water, because this is where intuition starts to protest, and that's usually a good sign. Up to now, we've been talking as if there's a clean separation between three things: the system being studied, the measuring device, and the observer. That separation feels natural because it matches how we talk about the world. There's out there, and then there's me, and somewhere in between are instruments doing honest work. But quantum mechanics has an annoying habit of ignoring our preferences. According to the equations, everything involved in an interaction, particle detector, air molecules, photons bouncing around, even the atoms in your retina, is just one big quantum system. No dotted lines, no privileged boundaries. If you write down the equations honestly, the measuring device doesn't force a result. It becomes entangled with the system. The particle and the detector stop having independent descriptions. Instead, you get a joint state particle here with detector, click, particle there with detector, not clicked, and so on. All at once, perfectly legal, perfectly smooth, no collapse required. And here's the kicker: that joint state still contains all the possibilities. So if you follow the mathematics faithfully, measurement doesn't end the story, it multiplies it. That's deeply unsettling if you believe that physics is supposed to explain why you saw one definite thing. Because now the theory is telling you that, at the fundamental level, nothing singled out that result. Everything just kept evolving. At this point, you might be tempted to say, fine, the wave function isn't real. It's just a tool. The real stuff is classical, and quantum mechanics is just about our ignorance. That was a popular move early on. It feels comforting. It puts reality back where we're used to it. But nature doesn't cooperate. Bell's theorem and the experiments that followed shut that door pretty firmly. You can't keep reality classical underneath and still get the correlations quantum mechanics predicts. The universe violates inequalities that any classical, hidden description picture would have to obey, and it does so cheerfully over and over again in laboratories all around the world. So the strangeness isn't optional, it's mandatory. Now here's where Feynman's instinct really mattered. He didn't like explanations that swept confusion under the rug by renaming it. He wanted to know what the theory was actually saying, not what metaphors made us feel better about it. And what it seems to be saying, if you strip away the stories, is this: the fundamental description of the universe is not about what is, but about what can be correlated with what. That's a subtle but radical shift. Instead of asking, where is the particle, the theory asks, a If you do this experiment, what result will you be able to correlate with that setup? Instead of describing objects with properties, it describes relationships between possible observations. That works beautifully until you remember that relationships don't experience anything. You do. Let's sharpen the knife a bit. Consider time. In the equations of quantum mechanics, time plays a very peculiar role. The wave function evolves smoothly and reversibly. In principle, if you knew the exact state, you could run the equations backward just as easily as forward. There's no preferred direction. No special moment when the universe says, okay, that's the present, but your experience of time is nothing like that. The past feels fixed, the future feels open, the present feels like a knife edge where possibility turns into fact. That feeling is not in the equation, so we add stories. We talk about entropy increasing, about memory formation, about irreversible processes. All of that is important, and much of it is correct, but notice what it doesn't do. It doesn't explain why one moment is being experienced rather than all of them. It explains why records persist, not why awareness feels pinned to a moving now. The same gap again. Now let's make it even more uncomfortable. Suppose you accept, for the sake of argument, that the wave function is real, not a bookkeeping trick, a genuine description of the universe. Then the universe fundamentally is not a collection of things in space. It's a gigantic vector in an abstract space of possibilities. That's already strange enough. But now ask yourself, where are you in that description? Are you a particular configuration of particles? That won't work because the configuration itself is spread across alternatives. Are you the whole wave function? That seems excessive. Are you something outside the theory entirely? That feels like cheating. No matter where you try to put the observer, the theory resists being closed neatly around them. This is why people sometimes say consciousness causes collapse. It's not because there's evidence for it. It's because they've run out of other places to put the missing piece. When every physical process seems to follow the same quantum rules and none of them produce a unique outcome, the temptation is to smuggle in something non-physical and hope it does the job. But that move creates more problems than it solves. What kind of consciousness? Where does it come from? Does a cat collapse a wave function? A bacterium, a thermostat? You can feel the explanation wobbling under its own weight. Feynman was allergic to that kind of hand waving. He preferred to sit with the discomfort, and sitting with it leads to a peculiar realization. The theory never promised to explain why this experience happens. It promised to predict correlations between experiences. That's a weaker claim, but one it fulfills spectacularly, which means that the hidden gap may not be a bug. It may be a boundary, a sign that physics, as currently formulated, is a theory about structure, not presence. Think about it this way. A map can tell you how cities are connected, how far apart they are, what routes exist between them. It can do all of that without ever explaining what it feels like to stand in one of those cities, breathing the air, hearing the noise being there. The map isn't wrong. It's just not the whole story. Quantum mechanics may be the ultimate map, incredibly precise, incredibly reliable, and completely silent about what it's like to inhabit one of the points it describes. That silence is easy to ignore if you're focused on calculations. But if you listen closely, it's deafening, because once you notice it, you start to see that the definite world you experience, the one with outcomes, moments, choices, is not something the theory builds. It's something the theory assumes, and assumptions are invitations. They invite you to ask whether the sharpness of reality, the fact that something happens rather than everything happening at once, is a fundamental ingredient of the universe, or an emergent feature of how information is organized, or something tied to the very act of being an observer at all. By the time you get here, you're no longer asking, what is a particle? You're asking, what does it mean for anything to be real? And if you're honest, you have to admit the equations don't answer that. They dodge it gracefully, like a skilled conversationalist changing the subject. But maybe, just maybe, that dodge is telling us something important. All right. Then let's follow that dodge to its end. Because sometimes what a theory refuses to say is more revealing than what it shouts. By the time you've stared at this long enough, something subtle happens to your intuition. You stop expecting the universe to behave like a well-lit room full of furniture where every object has a location, a label, and a job description. Instead, it starts to feel more like a story that only becomes concrete as it's being read. That's not poetry. It's a technical observation wearing a poetic coat. Think about this. Before you open a book, all the pages exist. Every word is already there. But the experience of the story, the suspense, the surprise, the meaning, only unfolds one sentence at a time, in a particular order, from a particular perspective. The book doesn't force that perspective. The reader supplies it. Quantum mechanics looks uncannily like the book. Your experience looks uncannily like the reading. The wave function contains an enormous structure of relationships. Who can correlate with whom? What outcomes are compatible with which setups? How probabilities flow from one situation to the next? It's rich, precise, and global. But nowhere inside it is a little arrow pointing to now. Nowhere does it say, this is the outcome being lived. And yet, here you are, living one. The temptation is to ask, so is reality incomplete? But that might be the wrong question. A better one is incomplete for what purpose? If the goal of physics is to predict experiences, then quantum mechanics succeeds spectacularly. If the goal is to replace experience with equations, well, that was never on offer. We just quietly assumed it. Feynman had a way of noticing assumptions like that and smiling at them, the way you smile when you realize you've been holding your keys the whole time you were looking for them. The mystery wasn't that quantum mechanics was weird. The mystery was that we expected it to explain something it was never designed to explain. And here's the existential turn that sneaks up on you. The gap, the one we've been circling this whole time, may not be a hole in the theory. It may be the place where theory ends and existence begins. Not because existence is mystical or unscientific, but because description and presence are different kinds of things. No equation, no matter how beautiful, ever happens. It just is. Happening seems to require a point of view. Now be careful. This doesn't mean the universe needs you in particular. It doesn't mean consciousness is a magical force pushing particles around. It means that the universe, as described by physics, is a structure of possibilities, and that actuality is something like selecting a path through that structure, not selecting by force, selecting by being. When you think about time this way, something clicks. The reason the present feels special isn't because the laws of physics privilege it. They don't. The equations are perfectly happy without a now. The present feels special because it's where experience is occurring. It's the page you're currently reading. The past is fixed because its pages have already been read. The future feels open because its pages haven't. The wave function in this picture isn't marching forward in time. It's the whole book laid out at once. And that makes the quantum truth Feynman glimpsed easier to say, though no less unsettling physics tells you what can happen. It does not tell you what it is like when something does. That what it is like may not be reducible. Not because we're ignorant, but because reduction isn't the right tool for that job. This doesn't diminish physics. It elevates it. It tells us exactly what kind of explanation we're holding. A structural one, a relational one, a map of possibility space so accurate that it powers civilizations, yet humble enough to stop short of claiming it contains the feeling of reality itself. And here's the quiet punchline. Once you accept this, the world doesn't become colder or more mechanical. It becomes stranger and, in a way, more intimate. The fact that there is a definite experience at all, that something rather than everything is showing up, stops being an annoying technicality and starts looking like a fundamental fact of the universe, not explained away, not denied, simply acknowledged. The hidden gap, then, is not a failure to be embarrassed about. It's a signpost. It tells us where calculation ends and wonder begins, where prediction gives way to presence, where the universe stops being just a set of equations and starts being lived. And maybe that's why Feynman, for all his precision and impatience with nonsense, never tried to seal that gap with easy answers. He seemed to understand something important, that a theory which explains everything except the fact that something is happening at all might be doing exactly the job it's meant to do. After all, if physics could explain experience completely, there would be nothing left to experience. And then who exactly would be doing the explaining?